Hello and welcome to a very special Cracking the Cryptic Patreon reward video explanation. So here we're going to be looking at the March 2021 reward Sudoku Hunt, the new 7 wonders of the world, which was based on those new 7 wonders and took us on a quick tour of the world through puzzles related to them all. What I'm going to try and do now is to explain to you how they were all solved individually and how you could then piece together the answers to solve the final 8th puzzle, and how from that you could generate the 7-letter word that these instructions said were required. So those are the instructions. Let's have a look at the first. Actually, what we're going to do is I'm going to be trying to use my editing skills to cut between a video I made about a month ago when I had created the puzzles for the first time and was testing them. So what you'll see in that is my solving the puzzles in 5 cases. But 2 of the puzzles changed fairly significantly, so I'm going to resolve them now, and you'll see that on this video cut in with the solutions to the other puzzles. So I might make reference, and this is me from a month ago, to a slightly different version of the document, but the puzzles that you see me solving should have been the final versions, because for the 5 puzzles that we go back to my old self, they didn't change. So the first puzzle, in fact, the first 3 puzzles were all unchanged, and I will now, you'll see me taking you through the Colosseum, the Great Wall of China, and the Taj Mahal. And we get some facts about the Colosseum, which are very similar to the Wikipedia page, are taken directly from the New 7 Wonders of the World website, and contain nothing about the puzzle at all until the paragraph in which the rules are described. Equal sum cages. Each cage has the same total. The cages situated on the oval, the yellow cells, each contain a different group of digits. The cages on white cells also each contain a different group of digits, though the same group may be used in a white cage and a yellow cage. So that's the rules. I hope they're understandable. They may, of course, have been adjusted, but the point is that in the whole grid, all of the cages have the same total, and we have to work out what that is. But the constituents of each cage, in the yellow, first of all, and in the white separately, are different. So there we go. Now, the first thing to do, after admiring how we have drawn an oval to represent the Colosseum, is to work out what is the common total of all the cages. And the best clue to that is in box 9, I think, where there are 3 complete cages and 1 other cell. So the 3 complete cages could add up to 42 if the cage total was 14, 39 if the cage total was 13, or theoretically 36 if the cage total was 12. However, in those latter 2 cases, this digit would be a 6, which is impossible, or a 9, which is impossible. So these 3 must add up to 42 with a 3 here. The common sum for the cages is 14, and we know therefore that there are going to be, first of all, in the yellow circle, in the yellow cells, 14 different 3-cell cages. Now, I think the best way to kind of operate with this is to work out what all the sums are. So we could have 1, 4, 9 makes 14, 1, 5, 8, 1, 6, 7, 2, 3, 9, yeah, that works, 2, 4, 8, 2, 5, 7, 3, 4, 7, and 3, 5, 6, and nothing else will be possible. And that is, of course, 8 different cages And we have 8 different 3-cell cages in the yellow cells. Now you will also notice, if you count up the white cell cages, we have, and they're looking specifically at the 3-cell ones, 1, 2, 3, 4, 5, 6, 7, 8. So again, we have 8 3-cell cages in the white. So let's make sure that we are counting them off in each type. Now in the white, we also have 2-cell cages. And of course, 14 has 2 possible 2-cell resolutions, which are 9, 5 and 8, 6. Now this pair obviously can't be 8, 6 because of that 6 and indeed that 8. So that's the 9, 5 pair. 8, 6 goes down here. We can tell from that 6 which way round they go. And we've got our 2-cell cages filled with candidates. Now 4-cell cages aren't going to be so useful. There's only 2 of them. Am I missing one? No, there are only 2 of them. So that's out of, I think, at least 5 possible combinations. So that's not so helpful. So now we're going to have to do a bit of either planning or Sudoku. We could look at these cages and wonder what they are, but there are different alternatives. They could be 149 and 257, or they could be, could they be anything else actually? Maybe I'm wrong. Yeah, what will the 1 go with? Must go with 4 and 9 because it's not allowed to go with 6 or 8. So these must be 149 and 257, but we don't know which is in yellow and which is in white, so it's not so straightforward for us. So what can we do at this point? Well, there are a number of sums that we can look at. So first of all, up here we've got 2 cages that are 28, plus 7 is 35. These 2 must add up to 10 to make the 1 to 9 total of 45. And if they're 10, they're either going to be 1, 9 or 2, 8. If they're 2, 8, the 2 can't be in column 3 where that 2 is already sitting. But anyway, now we know this cage is 14, 6 is 20, 7 is 27. These 2 add up to 10. That's 37. This cell, take 37 from 45, you get 8. 14 plus 14 plus 8 is 36. These 2 must add up to 9, and they don't use 8, 7 or 6. That's a 5, 4 pair right there. That 8 has ensured that 8, 2 is not possible there. We've got a 1, 9 pair and a 3, 2 pair to complete the row. Now, here in this box, we've got an 8, 4, 5, and we've got 1 in there. Does that allow us to determine the cage? Yes, it does. This white cage has to be 1, 6, 7 because 1, 5, 8 and 1, 4, 9 have been ruled out. So that's 1, 6, 7, and we're going to just X it because we've put an X in it, because we've placed X in the white. So that's sorted. Now that means this is 2, 3, 9, and we've done one of the yellow cages with a 2, 3, 9. We can put an X there. Let's see what else we can do with that. Right, the 5, 9 there and the 9 here says we know where the 9 is. That's there. The 5 there also resolves the 4, 5 cage. And as we look down this column, 4, 5, 9, 8 gone. We've got 1, 2, 3, 6, 7 still to place. Okay, I don't know how to do that, but let's have a look at this box. It's an interesting one. We've got a 14 cage there, 6 there, that's 20. Now in this cage we have another 8 to fill, that's 28. Now these other 3 cell, 14, 20, no, we have 11 to put in that cage. It's a 14 cage, I'm sorry about that. 11 and 6 is 17 and 14 is 31. These other 3 cells add to 14. So they form a sort of virtual 14 cage, but what that means is that as these 3 cells also form a 14 cage, this must be the same as this. So I'm just going to colour those blue because that looks quite useful. This one can't be 4, 5, 9, 8 or 6. This one can't be 2 or 3. So these 2 are 1 or 7 as a pair. We don't know which yet, but that's quite interesting limiting information. Now, if they were a 1, what would we be putting here? It would have to be 4, 9. That would work, I think. Yeah, we're not able to put 5, 8 or 6, 7 in those. So that could be 1, 4, 9. If it's a 7, then we can't use 7, 6, 1. But we could do 7, 2, 5 or 7, 3, 4. Okay, that's not certain. Sorry, I was just hoping that would work. Let's have a look at this cage. How about that? 2, 3, 6 are gone. So it's in the yellow. 1, 4, 9, 1, 5, 8 are the only possibilities. So it's got to have a 1 in it, and that's clearly got to be in this cell. These can be either 4, 9 or 5, 8. If they're 5, 8, we know which way round they are. Now that 1 doesn't help there. Doesn't necessarily help here either. So 7, 4, 3, no, I don't think we can do anything with that 1 actually, but at least we found it's there. Now, what else can we do? 6. Yeah, 8's quite interesting. We've got these 2 8s here. So 8 is in one of these 2 cells. Can it be here in a 14 cage that's 4 cells? Well, it would have to be 8, 2, 1, 3, which would put 2 here. Yeah, that is just possible. So we can't rule that out yet. Let me see what else we can do. We've got a cage down here that can't have an 8 or 6 in it in the white. Could still be 1, 4, 9, just. 2, 5, 7 and 3, 4, 7 are also possible, so not that useful. Now, okay, let's see what else we can do, because I can't particularly remember a route through this from here. I know there is one, or I believe there is one. Now the 3 here, what's that going with? Maybe I should have looked at that. 3, this is in the white, so it could be 3, 2, 9 or 3, 4, 7. So let's put those possibilities in. And if it was 3, 4, 7, that would be a 1. These 2 would have to add to 13. They would be impossible. That's quite interesting. Yeah, if that was a 4, 7, we'd use the 1 here. That would become a 1 because they're the same. These 2 would have to add to 13. 6, 7, 8, 5 and 4, 9 have all become impossible. So that can't be a 4, 7 pair. It must be 2, 9. 3, 2, 9, 8, 6. So we have 1, 5, 4, 7 to place. Now 2, 9 there. Right, we know what these 3 cells add up to because we've got 5 here, 14 in the cage and 6. That's 25. These 3 add up to 20. Now we can see, because of these cells, that they don't have a 9 in. So therefore they must be 8, 7, 5. And this one can't be 7 because of the 6, 7 pair here. If they're 5, 7, 8, we can take 5 and 8 out of that pair. They become a 4, 9 pair. We can tick off the 1, 4, 9 in the yellow. That's been done. Now, can we use that? We must have a 4 down here. That's an absolute certainty in the column. So we've got a white cage which needs a 4. Can it be 4, 1, 9? Yeah, that's possible. Can it be, it can't be 4, 2, 8, and it can't be 4, 3, 7. So it must be 4, 1, 9. So that's all resolved. Let's take out the pencil mark, put in a 9 here. So we've got 1, 4, 9 in the white. Let's not forget to tick these off. We're obviously in this box going to have 2, 5, 7 in the yellow. So we'll tick that, pencil mark it in. Now we've got a 1, 4 pair there looking at this cell, so it's clearly a 7, and we'll remove the colours as we put it in both blue parts. That 7 places the 7 in the top box. In the right mode, that takes 7 out of that cell. Now the 9 down below has fixed that as a 4-9 pair. Now what can this be? Not using 4, 7, 9 or 6 in the yellow. Well, it looks like 1, 5, 8, and it has to be. So we can mark that in the cage. We get a 3, 4 pair here, which is resolving a lot of the stuff in boxes 6 and 9 at this point. So no 2 there, 2 is there. And we've got reduced to pairs and 1 triple in boxes 3, 6 and 9. We've also used up several, especially of our yellow cages. So we've still got 1, 6, 7, 2, 4, 8, 3, 4, 7 and 3, 5, 6 to go. Well, what can go in here? It can't have a 1 in because of the position of those ones, and it can't have a 7 in. So in fact, it now has to be 2, 4, 8 or 3, 5, 6. Whoops, my apologies. If it's 2, 4, 8 or 3, 5, 6, this one has to be 4 or 6. 2, 4, 8 or 3, 5, 6. Yeah, okay, that's not resolved as I'd hoped. I might look somewhere else actually. Let's 6, no. This, yes, okay, that's quite interesting. So we still have 2, 4, 8 to fit in somewhere. Where in the yellow can we put 2, 4, 8? Not here because of the 8. Not here because the 2s prevent a 2 being in that cage at all. Not here, again, a 2. So 2, 4, 8 has to be up here. And we can actually place that all. And that's really advancing us significantly. So 2, 4, 8 is placed. We've got no more 2s to put in the yellow cells. What do we have? I don't know, we'll get to that in a moment. We get a 3, 5, 6 set in the white up here. 3, 5, 6 is done in the white. And what else can we get from this? 9, 8, 2, 5, 7, 3. So we still have 1, 6, 7, 3, 4, 7 and 3, 5, 6 to place in yellow. Don't think we can make much advance on that. Now we've got 8s there and an 8 there. So 8 turns up in this white cage, which is either 2, 4, 8 or 1, 5, 8, therefore. 9 must be in one of these 3 cells. That's not all that helpful yet. 7 is in one of these 2. That's quite interesting. How could 7 be there? Well, this would have to be 1, 2, 4 in that case, which is possible with an 8 here and a 3 here. However, if this was 7 with 1, 2, 4 here, the 2 would have to be here. As we've just seen, that would put a 3 here and make this cell impossible. So 7 is not in the 4 cell cage. It must be sitting there. Where, what do we need? 3, 4, 7 or 1, 6, 7. Well, interestingly, neither of those can be a 6 because of the positions of 6. So that's a 3, 4 pair. The 3, 4, 7 yellow cage is done. We've just got 3, 5, 6 and 1, 6, 7 to place in yellow. So that is either 3 or 7 based on that information. 3, 5, 6. 3, 5, 6 and 1, 6, 7. So a 6 is repeated there. So one of these is a 6. Therefore, one of these 2 cells is a 6. Since it has to be twice in those cages. Not sure exactly how that's going to go down yet. Let's have a look. Maybe what else can we do in the white? Have I missed marking any cages? Yes, we've done 3, 2, 9 over there and 3, 4, 7 there. So I hadn't marked those off. And actually white is down to 3 cages as well, therefore. 1, 5, 8, 2, 4, 8 and 2, 5, 7. Well, that one can't have an 8 in it, so it's 2, 5, 7. Let's take out the 9 pencil mark there. That 2, 5, 7, 8, 6. This becomes 1 or 9, which forms a pair with that one in column 2. 2, 3, 4, 7. We've got 5 or 6 here, and the 8 in the column must now be right here. So that removes that pencil mark. That can't be with a 9 in its cage, so we know where the 9 is. And we're moving. 2 can't be there. Now, what are the yellow cages we have left? 1, 6, 7 and 3, 5, 6. They both look possible there still. 2, 5, 7. So we've got a 1 or a 3 here. 1 or a 4 here. Actually, that's a 1, 4 pair in the bottom row, so that is now 3. That's interesting. That makes this a 7. And we now know that's the 1, 6, 7 cage, and we've got the 3, 5, 6 to mark in box 7. This is the 3, 5, 6, and we can put the 3 in. The 7 there has fixed this pair. The 1 in that pair has fixed this pair. We get a 2 here. That's 10. 4 there. Neither of these can be 7, so the 7 in the cage is there. We get a 1 to finish the box. Now in the white, we've just done a 2, 4, 8 and a 2, 5, 7 cage. So the last one we can put in is 1, 5, 8, which must be this pair. Gives us a 6 and a 5, 9 here. Now we're almost finishing off. 5, 9 pair there. That fixes the 2, 9 pair. The 3 down here is fixed 2 and 3. 6 and 7 are resolved. This must now be a 1. This 2, 5 pair is resolved. That gives us a 4 to finish the box. 3 and 8 now in the column. And a 1, 2, 4 set here. In fact, we know the 2 is there, given we've got all the other 2s in the grid. So 1 and 4 are a pair there. And we've got 1 or 5 here and 1, 5 or 6 here. So all the candidates marked, but actually there's a 5, 8 pair in this box already. So we can do 1 there, 6 there. Now we can't have an 8 here, or we've blown the total. 6, 1, 4, 3 does add up to 14, which was what we needed. And we can finish off. And that is the solution to the Colosseum puzzle, which we can bank for now and use later. So just 1 triple and 1 double to unwind, 6 and a 5. There we go. Let's test it out. Looks good to me. So that gets us through the Colosseum puzzle, and not too hard. We had to do the steps of figuring out what the common cage sum total was, and then getting a start with some maths in the boxes where the amounts were restricted, particularly boxes 1, 2, 3 and 9. Those were very much, I think, the keys to getting going on that one. Maintaining a list of the possible cage totals was also pretty much vital there. So it didn't take long to make, but it certainly helped to create that. If you can juggle all those in your head, you're doing very well indeed. So that was the Colosseum puzzle. We move on to the Great Wall of China. For these purposes, I'm not going to marvel at the wonders. I'll read the information, which is a relief in this because I could then mispronounce every single Chinese word there. We're just going to read the instructions for the puzzle. Chinese whispers. Any 2 neighbouring digits connected by the line must have a difference of at least 5. Now, fun fact, what's now known as German whispers used to be Chinese whispers because the first known appearance was on a map of China, or in a Chinese competition at least, maybe that. And then the idea was used in a map of Germany puzzle in a German competition and became known as German whispers, which actually stuck rather strangely. So there we go. And this means that along this line, any 2 digits must have a difference of at least 5. Now, it's an interesting rule set. The most interesting thing to learn from that is that 5 can never appear on the line, because 5's differences with 5 are to 0 and 10, not Sudoku digits. So 5's never on the line, and in fact the line must alternate between high numbers and low numbers. Now, I don't know which is which on this line yet, but I do know that the line must alternate between high numbers, which are 6 to 9, and low numbers, which are 1 to 4. So I'm going to mark the different parities. I don't know what they are yet because we're not given any digits on the line. However, we have to work that out. Now, it's also worth knowing that 6 and 4 can never appear in a place where the digits flanking them are seeing each other. So this cell here could never be 6 or 4 because 6 has a difference of 5 from 1, but on the other side it needs a different digit, and there is no other digit in 1 to 9 that 6 has a difference of at least 5 from. The same is true for 4. It can have a 9 one side but not the other. So there are various places along this line that 6 and 4 can never be in, and that's going to be worth bearing in mind. I think I've tried to highlight them, but you will probably understand the point. So, tiny bit of ordinary Sudoku first. The 5 in column 3 has to be here. The 3 in box 9 is in one of these two. There's not much we can do with regular Sudoku, to be honest. 7 is in one of those. 6, perhaps interestingly, is in one of those cells. And we'll get to that maybe in due course. Now, what's worth noting about the marking into high and low cells, which we don't know which way round they are yet, is that in row 4 there are 4 blue cells, and in row 3 there are 4 orange cells. So in both of those rows, either all the high digits or all the low digits, of which there are only 4 of each, are being used up. Now, which way round is it going to be? Well, it's worth noting that in row 4, these 2 digits are some of those that cannot be 6 or 4. Therefore, in row 4, one of these is 6 or 4. Now, 6 or 4, wherever it appears, must be flanked by either 2 1s or 2 9s. And that means that this digit has to be 1 or 9. If it was a 6 in one of these cells, then 1 and 1 there, if the 6 was there, say, would have to appear. If 6 was there, 1 and 1 there. If 4 was here, 9 and 9 there. If 4 was here, 9 and 9 there. Now, we can see very clearly that this can't be a 1, so this must be a 9. And that means 4 is the number. We now know that the orange cells are the large numbers, the blue cells are the low numbers. 4 must appear, can't be there or there. By Sudoku, it can't be there, so 4 is here in row 4. That makes this one a 9. We don't know about 6 yet. This could still be 6 with 1s either side, but 6 could also, actually no. Sorry, the orange cells are 6, 7, 8 and 9. And 6 can't be in box 1 or box 3 on it. So that's 6. 7 and 8 to place. We can do that by regular Sudoku, and the high digits in row 3 are placed. Now, next to 6, we have to have a 1, both sides. We've got 2 and 3 left to place in row 4 on the blues, but 7 means that 2 has to be next to it because it has to have a difference of at least 5. 3 there. Now, what numbers are 5 higher than 3, 8 and 9? 5 or more higher than 3, obviously. So that's gone in. There's one more orange cell in this column. That's got to be the 6, and that's got to be flanked by 1s. This one has to be 5 lower than 8, and it can't be 3 or 1, so it's a 2. This one has to be 5 higher or more than 2, and it can't be 7 or 9, so that's an 8. This one now has to be 3 because it can see 2 and 1. This one has to be 9 because it can see an 8. And finally, this one we don't actually know for sure. This could be 2 or 4. But that deals with the whole of the Chinese Whispers line. So I'm going to uncolour it all now because the colouring has served its purpose. And now we're just solving as regular Sudoku, aware of that being either 2 or 4 for the rule. So 5 in column 7 must be there. We can, column 8, we can place the 2 and 4. 3 there. We've got 7, 8 and 9 still to go. Let's just take out those marks. Pairs in each one. Up here we've got 3, 7, 5, 2, 8, 6. That 1 tells us where the 1 is. Then we get a 9, 4 pair, which is resolved. That fixes this triple we created in box 9. Now in row 8 we can do the 7 and 6. 2 there, 4 there, 8 there. We've got a 2 and a 1 to finish box 7. 4 to finish column 2. We've got 2, 8 and 3 to place. 2 must be there because of this 2. We can do 3 and 8, and all the corner boxes are suddenly done. 5 there in row to complete row 3. 6 and 1 to complete column 1. We've got 2 and 5 to complete column 9. 1, 2, 4 across the top. Yep, they're write-ins as well, thanks to having all sorts of digits looking at them. Now we have 6, 7, 9 across the bottom. We can place 9, pencil mark 6 and 7. This set of 3, I can see 1, 9, 4, 5, 3, 7 looking at them. So it's a 2, 6, 8 triple with 2 there. In fact, we can do the 6 and 8 as well. 9 and 4 can now be placed in the row. We've got 7 and 8 to place in row 4. That might have been an easier way to start these central 3 boxes. 6 and 4 there. We've got 3, 5, 7 to go in here. We can do the 5, 3, 7 pair, as we notice that the 6, 7 pair can now be resolved. That resolves the 7, 3 pair. And finally, the top section. So there we go. That one is not too bad for a German Whispers or Chinese Whispers style puzzle. Yes, you do have to do the understanding at first about rows 4 and 3, which are very much the key to the puzzle. But once that's done, well, it didn't take long to work through either the line once there was the start here, or the rest of the puzzle after that. So as I say, for a Chinese Whispers or German Whispers style puzzle, not too bad at all. Hooray. So we can move on to the next puzzle. Taj Mahal. I hope it was a recognizable version of the Taj Mahal from the lines drawn. Now this is a thermo Sudoku with a very slight twist. Well, 2 very slight twists perhaps from the normal, in that we have the ends of thermometers are marked in this one as squares, and we also have some letters in the grid for which consonants represent odd digits, which is rather unusual. So they're all in the top row. Let's immediately note that there are 5 consonants in the top row. So again, we can use a bit of parity. They must be 1, 3, 5, 7 and 9. The other cells in the top row, 3 of which have A's, but that's not really relevant to the puzzle and wasn't mentioned in the rules. They must be the even numbers 2, 4, 6 and 8 in this case. Now this cell is the first in a 4-cell thermometer, so it can't be 9 or 7. This one is the last in a 4-cell thermometer, so it can't be 1 or 3. Same over here, but we can't do much more with the letters than restrict the numbers to that. The actual places to start in this puzzle are in boxes 7 and 9. Now here we have symmetrical but slightly different properties going on. So the simplest question to ask in box 9 is, where can the 1 go? Well, it's got to be on a bulb if it's on a thermometer, so that's got to be there. The next corollary question is actually, where can a 2 go? Which is quite interesting because on these thermometers, 2 can only be in one of the first 2 cells. Once you get here, it's the 3rd highest number in the thermometer. That can't be a 2. So 2 must go there. The final question the third question I'm going to ask about this box is where can 9 go? Well, 9 always has to be on the end of the thermometer. And then where can 8 go? Well, 8, again, these are now thermometers where we've basically got to find the highest possible place to put the 8. That has to be there. Nowhere else can 8 be, or it would need another number in between it and 9. So we don't know where 7 goes, but it must be next to the 8 on one of the thermos. So I'm going to pencil mark it there. Another question is, where does 3 go? And 3 can't be this far along either of these thermometers because it's the 4th highest number. So 3 must be in one of those. At that point, I'm going to stop asking questions about this box and move it over to box 7, where again the 1 and the 9 questions are exactly the same and we can fill them straight in. Now this time it's not where does 2 go, but where does 8 go? And that goes here. Then we can ask about 2, that must go here. 3 must be next to 2. 7 can't be right next to 2. It's got to be, 7 can't be more than 3 away from the end here. So it's got to be in one of these 2. Interestingly, the 7 there must have an 8 above it, which must have a 9 above it, in whichever stalk of this thermometer that's the case for. The same is true for 2 and 1 over there. So I'm going to pencil mark those as well. Now, there is a little bit of juggling to do now. How are we going to work out what other numbers go in boxes 7 and 9? And it gets quite interesting when you start asking, start looking across the 2 boxes at each other. So another intriguing question though is, where does 4 go in this box? And you might say, as far as these are concerned, well, it could be under the 3 in either place, or it could be there and the 3 would be on the other stalk. But actually that gives us a problem in this box. If this was 3 and 4, these would be 4 numbers, in one case below 4 and in the other case below 3. So above the 3 you'd have to have 2 and 1. Above the 4 you could have a 3, but then you'd have to have another one of 1, 2 and 3, and that's impossible. So in fact 4 cannot be in these 2 cells and must be below the 3 in one of the stalks of this thermometer. The same is true over here. Where can 6 go? If it went in one of these cells with the 7, then you cannot fit. You can put 6, 7, 8, 9 in those cells, but one of the 6 there is going to be above either a 7 or a 6, which is not allowed. So 6 must be below the 7. So, I mean, it's an intriguing sort of way that it works generally. Now, what can we do with that information? We can start wondering about things like 5s across the box. Let me just work it out for myself. Ah, yes. 3 and 4 are either there or there. Now, if they're there, 5 must be here. If 3 and 4 are here, where's 5 going to be? Either there or there. So 5 is restricted to those 3 cells. Over here, I think it's the same story. Where can 5 be? And let me just work it out again. If 7 is definitely above 6 for the same reasons as 3 is above 4 here. So 7 and 6 could be there, in which case 5 is here. Or 7 and 6 can be here and here, in which case 5 is either here or here. So in either case, 5 is in one of those cells, not in these ones. Now, where can 4 be over here? Well, the interesting thing is that 4, we don't know from this box in its own right, but we do know from over here, where 4 is in one of those 2 cells, that 4 can't be here. So now 4 has got confined into those 3 cells, And as you can either see from the pencil marking, the only candidate left for this cell is a 6, or you can look at it as 4 and 5 have been restricted to those cells along with 7. So 6 and 3 must be in these two, but that is the way it works. So 6 goes there, 3 goes there. Now they're looking straight across here as well. So again, 6 is confined to those 3 cells now. And suddenly the only candidate here is a 4. So it's a weird symmetrical trip around the grid in a way. Let's just take out some of the possibilities we've left in. Now, 7 we knew had to be above the 6, and indeed, wherever the 6 is, it continues 7, 8, 9 up the thermometer. So that's now known to be there. We can take out these pencil marks and the 7 there. Wherever the 4 is, has to have 3, 2, 1 above it, so we can fill them in. Take out these pencil marks and the 3 pencil mark there. And we're left with this 5, 6 pair possibility and a 4, 5 pair there. You could ask something like, where does the 3 go in the bottom row now? It's clearly the smallest number in these 3, so it must go on the middle of this barbell sort of shape. That takes 3 out of the total. But let's look up the columns. We've got 1, 2, 3, 4 and either 5 or 6 here. So we can actually pencil mark all the possible digits as we go up. When we get to the top, it's either 8 or 9, but we know it's odd, so it's 9. This one is 5 or 6, so we can actually place the 7 and 8. Let's do the same up here. We've got 1 or 2, 2 or 3, 3 or 4. Got to be 5 at the top because it's odd. That sorts out the 4, 5 pair down below. We can look across and sort out the 6, 5 pair. That places that as a 6, and now we can go 1, 2, 3, columns 1 and 9, fully done. That 5 sees this cell. That's unsurprisingly a 1 at the top of the Taj Mahal there. We can take out 1, 5 and 9 from those, which are now a 3, 7 pair. Let's also just tidy up a couple of the even numbers that we can rule out. And let's look at the tops of these stalks. So this is now 1 and 2 are gone in the box. So that's 3 or 4. This is 4 or 5. Over here, this is now, has to actually be 6 and 7 above the 5, because that's the 8 and 9 are gone in the box. That's the only way to complete that stalk. This is a naked single 4. This becomes an 8 at the top. We've got a 1, 9 pair left in box 1. Here we have 2, 3 and 5, but 2 can't be there. 2 out of 2, 3 and 5 is the smallest number, so it must be on the bulb. And then we have a 3, 5 pair that we can't complete for sure. 4, 7 and 6 to go in up here. We now know it's a 7 at the top. That completes all our consonants. 4 and 6 to place there. And if that's a 5, it will have an effect on that, but we don't know yet. Let's have a look at column 3. No, let's have a look at where 9 goes in column 8. It's got to be there, basically. 9, 6, 7, 8. That can't... Okay, well, we'll move into column 3 now. I'm not absolutely sure what the order of this solve is from here. 3, 1, 2, 9. So we can start as low as 4 and go up as high as 8. So the possibilities are 4, 5, 6, 5, not 6, 7, 6, not 7, 8, due to this 6 and that 7. And in fact, that 6 is making that an 8. Sorry, I didn't spot that. 3, 8, 1, 2, 9, 4, 5, or 7 there. So the only place in this box for a 3 is here. 4, 5, 7, triple still to resolve there. 3, 5 pair over here. Right, let's have a look down here. We've got a 6, 7 pair on that dumbbell. 1, 5, 9 is that group. Now, what about this one? If that was even a 5, 6, 7, 8, 9, too many. So that has to be a 1. This, don't be suckered into thinking this has to be the 9. It could be the 5 at the moment. So we'll just take 1 out of those 2 cells. We've got 2, 4 and 8 to place here. This obviously can't be 8. But we can't do much else. But let's have a look at this longest thermometer in the grid. Now, I've done well not to actually mark all the possibilities from the get-go, as I would normally like to do. But anyway, this has to be 3, 4 or 5. Now we have a 4, 5, 6 triple across the middle, which fits in quite well with this thermometer. Excuse me. This now can be 5, 7 or 8, I think, culminating in 6, 8 or 9 in the end position. So we've got a 4, 5, 6 triple there. That's sorting out this cell, which can no longer be that since it's in the same box. That becomes 3. That fixes the 5, 3 pair. That 5 looks across at these and makes them 4 and 7 with a 5 there. This thermo means this is now a 4, which looks across and makes that 6. Now, various of the possibilities have come out of those. We've got a 4, 5, 6 triple still here. 3, we need 1 and 9 here. Well, clearly 9 can't be on the bulb, so that makes that a 9. We do get a 9 at that end, as you thought. This must now be a 3 since it's lower than a 2. 4, 5, 6, 3, 9, 1. We've got 2, 7 and 8 to place in the middle section. This can't be a 2. It's on the end of a 4-cell thermo. So the 2 must be here. That's part of a 7, 8 pair. At the top, we can rule 8 out of these now. That can no longer be 4, actually. That's even more helpful. We're down to a 4, 6 pair in the top row. We've got 1, 5 and 6 to place in box 3. We can do the 6. 3 in row 3, interestingly, can now only be here. That 3 is preventing it being there. That gives us this other number on the thermo as a 2. And this is now an 8, 7 pair because it's got a 5, 9 as well as all the numbers in the box already looking at it. So 8, 7 go in there. That's 9. This is 5. And that should allow us to sort out the rest of the puzzle. 5, 5, 5 must be there. Hopefully we're not using thermos anymore. Or are we? What am I missing for disambiguating the rest here? Thermo's not going to help there at all. 3, 9, 5. Oh, this is interesting. As I say, this is still in test, so there is a chance that I've managed to leave alternative solutions in at this point, which would be incredibly annoying and disappointing, but it does sometimes happen. So let me just study this a little harder, and I hope I'm missing something, although I can't imagine what I am missing. That's very interesting. I can't see how this can possibly resolve cleanly. Yes, I can. Look, 6 is an X-wing in those 2 cells. Oh, that's a relief. There must be another way to disambiguate that I'm also missing, but never mind. I'll use this. 6 in row 9 is in either column 4 or 6. In row 1, it's in either column 4 or 6. That must use up the 6s for columns 4 and 6, so this cannot be a 6. So we can put 4 in there. That sorts out the pair at the top. That sorts out the pair at the bottom. And these other cells do disambiguate, and that's a big relief. I was immediately starting to think, what can I do to disambiguate that? And with the thermos, it would be very difficult. Anyway, there we go. That is resolved, and too much relief. And now I'm back to talk us through Christ the Redeemer, which did change reasonably significantly after testing. So our tester Elias, or Elias, I expect it's pronounced, sorry, was very helpful and pointed out that it was too polite to say that the original version of Christ the Redeemer was not very good, but it was a bit trivial. There were many digits presented, and it didn't have any knight's move instructions at all, you'll be surprised to learn. So the version that we had to solve instead had these rules. Each digit in the statue area, which is white, has at least one consecutive neighbour there. Now, this wording caused some uncertainty, and I'm sorry about that. It was certainly intended to mean that there was one consecutive, for every digit in the white area, there was a consecutive digit also in the white area. That was what I thought there meant. Now, it turned out some people couldn't interpret there to mean like that, but luckily it didn't matter in terms of solving the puzzle. I think it may have made it a fraction easier to understand that, but it didn't actually matter in terms of getting a unique solution. And it certainly wasn't the part that gave people difficulties. That part was the second rule. Every instance of a digit, which is a knight's move from an identical digit, is circled. Now that's really quite important and carries a negative constraint in the wording there. It says every instance of a digit, which is a knight's move from an identical digit, is circled. So any cell with no circle, its digit cannot be a knight's move away from an identical digit. But any digit with a circle, its digit must be a knight's move away from an identical digit. So that's two sort of very conflicting instructions together. So let's have a go at the puzzle, which I haven't actually tried for about a month, but we'll see how we get on. Is it? No, it's not that one. It's this one. There we go. So this is Christ the Redeemer. And with those rules in play, let's have a look at the puzzle, see what we can find to do. Well, you can start, for instance, with 6 in row 7. Where does 6 go in row 7? So initially there are 3 cells that seem possible, but then the knight's move thing applies, and those 2 cells are knight's moves away from those 2 cells, and they do not have circles. So there can't be a 6 there, or there'd have to be a circle around that. There can't be one there, or there'd have to be a circle around that. So we can put 6 in there. And let's have a look around, see what else we can do. 6, by the way, is going to be one of those cells. Let's try and not forget the consecutive digits in the white rule, although we can't really use it yet. So, 2 is quite interesting in box 6. All those cells are ruled out by these 2s, by normal Sudoku. Those obviously can't have a 2 in as well. And this one is a knight's move away from this, which is not circled. So that can't be a 2 either. So there must be a 2 here. And interestingly, it must be a knight's move away from another 2. But we don't know yet whether that's in one of those cells, could even be there actually. So we can't use that. But let's think about this property of the circled cells having to be a knight's move away from another identical digit. This 9, for instance, where can its partner possibly be? Not in the same box, that breaks normal Sudoku rules. So it's got to be here. Where else are we getting digits? That 2 can reach any of those cells now. That one would conflict with the 2 we've put in. So we can't really do anything with that. This 4, again, there are possibilities outside its box. And the 1 as well. So there's not all that much to get going on here. The 5's down to only 2 possibilities, I think, outside its box. But one of the more interesting properties we can pick up on is that even though we don't know what digit this is, we know the only knight's move cell it can reach is that one. So let's colour them just to start with. The same here. That must be the same as that one. They're clearly going to be different from the blue. This one clearly has to reach here. And this one clearly has to reach here. So, sorry, the colours aren't maybe working brilliantly because of the orange shading, but those are all 4 pairs of digits that must be paired up somehow. And we'll try and figure out what those are as we go along. Actually, that has an impact on the 4, because earlier we were saying the 4 could be there. the knights move away from that. But in practice it can't, because that has to be the same as this, and that would clash with that 4. So that 4's partner must now actually be in this cell. We can put in a 4 there. Now we know that can't be a 4, but it doesn't tell us which of these cells. Actually, there's quite a few there that the 4 could be in, so we can't finish that off. Let's see what else we can find, though. And I think this puzzle is really a matter of just looking for things that you can find. 2s, we do have 2 2s here, but it doesn't work at all as well as the 6's example, because I think any of those could be a 2 at the moment. 5s, we have 2 5s here. 9s, yes, sorry, I should have worked on that 9 originally. Those 2 9s mean there is a 9 in one of those 3 cells. This 9 not having a circle means that 9 can't be in either of those, and we can place a 9 here. Now, let's remember that consecutive rule. This 9 has to have a consecutive neighbour in the white cells, and that's going to put an 8 in one of those 2. And that's quite interesting. What digit can go in here and have a neighbour here if that was an 8? It would have to be 7 or 9, but they've already been used in the box, so that can't be 8. So 8 must go in this cell. And this needs a knight's move partner. Could be there or there or there. We can't decide yet. We've also got this little run of digits here. That one must have a consecutive neighbour there. We don't know what it is yet, but let's bear that in mind. Now, 9 there and 9 there. So we need a 9 in one of these 2 cells. Which one can it be? If it's there, it's also there. And it would be here and here. And here, interestingly. And that would be fine. Just the... yeah, that would work okay. So we can't rule that out. 7. 7 in columns 2 and 3. Where's the 7 in column 1? One of those 2 cells can't be there because that would need a circle around it. So we can put a 7 in there. Now 6 can't be here because that would need a circle. So it's in one of these 2 cells. Then it's going to be somewhere up here. Could just be in the white with a 5 next to it, so I can't rule that out. What else can we find? I thought this was a little easier than this when I was first testing it, so let's see how that goes. 96. Right, 4 there. By ordinary Sudoku, those are ruled out. That can't be a 4 because it would need a circle, being a knight's move from there. So one of those is a 4, and the 4 in column 3, column 9 must be in box 3 up there. Lots of circles means that this sort of central torso area of Cristo Redemptor is not a very useful place to be looking for clues. It's much easier when you have cells where there are no knights moves away. Yeah, one of these 2 is 9. I should have pencil marked that. I'm going to do it now. This can't be 9 because this would have to be 9 as well, and that would stop both of those being 9. So that's not 1. That means 9 in box 9 is in one of those 3. Hard for me to see exactly how that's going to resolve. Be there. Okay, let's see if we can get something else going a bit more. It is a matter of looking for both the positive and negative constraints in this puzzle, weirdly. 2. That could be a 2. It must be up here with the 4 somewhere in column 9 at the top. Now what can this be? This is 7, 5, 3 or 8. Same as in there. So I'm going to pencil mark the possibilities. This one and this. 2, 6, 4, it can't be. Oh, there's a lot of possibilities it still can. This one, though, can't be 8, 5, 7, 6, 1, or 2, given where it's placed. Its partner is here, must be 3, 4, or 9. This one sees 7, 9, 2, 1, 6. Its partner is here. They must be 3, 4, 5, or 8. This one is, yeah, there's 6 possibilities for that, so that's not so easy to limit. Now, what about this 7? Don't know what to do with that, frankly. Interesting. As I said, I don't remember this being quite this difficult when I was creating it, so apologies if you had to struggle through it. It really is just a matter of looking for these things. Yes, 2 in box 7. Right, those cells are all ruled out by the positions of those 2s in ordinary Sudoku. Clearly can't be in those. So it also can't be here because that would need a circle, being a knight's move from there. So we get a 2 in there, which fixes the 9. That gives us that as a 9. 9 in row 7 must be here. That gives us 9 in column 7. And suddenly we're on a roll with the 9s. I think we've got 8 of them placed now, so there must just be 1 left in box 5. So all the 9s suddenly done. And this is the good thing about the puzzle, is once you get on a roll, it gets a bit easier. So 3 or 8 there, 3, 7 or 8 there. 1, 3, 7 or 8 there. That's not so helpful. 7, 9, 2, 6, 1. Right, what can be a 5 down here? Oh no, 4 is ruled out of those cells. So 4 has to be in one of those 2. Oh, and let's use the consecutive rule that I'd forgotten about for a bit now. So this 9 has to be next to an 8 in the white area. It's got to be in one of those 2 cells. Don't know which one yet, but I'm going to pencil mark that and hope I can remember that stretches across the box. This 9 must be next to an 8 as well. Now again, I don't know where that goes, but it does mean that this can't be an 8, which is connected to that cell. This 6 has to be next. This 9 actually has to also be next to an 8. They all look possible at the moment, so I haven't been able to use that quite as much as I was hoping there. That 4's been resolved. It's found a partner. It can have another one, but it's certainly got that one. Now this one, we were saying earlier there weren't many candidates, or there were too many. Now 2, 9, 6, 4 in the same column there. It also can't be 7 because this one would need a circle. So these 2 must be 1. They can't be 1 either. That 1 sees this. So they're 3, 5, or 8. 8 would be useful. It would give the 9 a neighbour. And indeed, it would then mean that these needed neighbours looking up. So what can this be? 1, 2, 6, 9. This has to be, can't be 7, because it would, again, have a circle. 3, 4, 5, or 8 there. This can't be 4, because it would need a circle. So one of these is a 4. But it should be that one. Nearly managed to rule out which it was. Right, 1. Those can't be 1. That's not 1. So 1 is in one of those 2 cells. Let's pencil mark that. And therefore one of these 2. Just trying to figure figure out if I know any more about it. Oh, in this column we've got 8, 6, 5, 7, 9, 2 there. So these are from 1, 3, and 4. Now, use that. Maybe the consecutive constraint. No, not really. 6 there. Now, wherever the 1 is here, it has to have a 2 next to it. Actually 2 and 2, sorry. That is in fact a 1-2 pair. That's the only place 1 and 2 can go. So unfortunately that resolves the neighbour issue for 1 and 2. They're all dusted there. 7, 6, 4, 9. We have 3, 8 and 5 to go in the remaining cells. This one can't be a 5. It would need a circle, so that's 3 or 8. With 3, 5 and 8 in these as possibilities. 5, 6, 2. 1, 2 pair. They don't have circles. 2 and 2. So one of these is a 2, definitely. Can we tell which one, I wonder? No, it's quite interesting. No, I was going to say, yeah, if that's a 2, there's a 2 here. But if that's a 2, there's a 2 here. So that doesn't actually get those resolved. Must be a 2 in these cells. Got one over there as well. Tricky, actually. This one needs a partner. It needs a knight's move partner, and it can't be here. And now that's gone, so in fact that must be a 2. So we will take 2 as a candidate out of those possibilities. And we've got 2, 9, 8, 7. Now this could be a 6. It would need a 5 here. 1 is not in those 2 cells. Now this can't be 1 anymore because it would need a 2 next to it in the white, and it can't have that anymore. So 1 is definitely in one of those 2. Therefore it's in one of these 2. Still scouring around for something that'll break the puzzle open a bit quicker. I think once we get on a roll, it should move fairly fast, but struggling to do that at the moment now. I'm just wondering where 1 is in this central box. Wherever it is, it has to have a 2 next to it in the white. And that might mean it has to be here. Since these can no longer be 2 because of that 2, then I think the only place that a 1 can be here and touching a 2 in the white cells is in one of these 2. So I'm going to fill that in as a 1-2 pair. That resolves the 1 in box 4. Gives us a 1-2 pair up the central column as well, which can't use the yet. Now, this is quite interesting. If this was a 1, it's seeing that. If it's a 2, it's seeing that. Okay, that didn't resolve that. Right, 8 now can't be in those 2 cells. So it must be in one of these 2. That can't be an 8 as a consequence. 8 is definitely in one of those over here. Got 4 and 3. That can only be 3 or 6 now. It does have a knight's move partner. There or there. Has to be in another circle, of course. 6, 5 has to be in one of these cells. Can't prove which yet, I don't think. This one seems to be 3, 4, 6. That's 3, 4, 8. This one, not sure. Right. Now maybe there are other circled cells that can't reach many Knight's Move partners. Now look at this. Where's its Knight's Move partner? It can't be in the same box. So it would have to be in one of those 4 cells. There is only one of them circled. Sorry, I should have noted that. Those two have to be the same as each other. So we can fill in 4 there. Now that's not 4. That places 4 in box 4 here. That sorts out 6. We've got a 3-8 pair. This must be a 7 as a result of that. And then these 2 cells are also a 3-8 pair. Can we go further? This one's in a circle. No, I don't think we can. Those are from 3, 5, and 8. Definitely include a 5. Now we've had the 4 here, so this is now a 1-3 pair. We have 4, 5, and 6 to place here. This one is, interestingly, it can't be a 6, and it also can't be a 4 because it would need a circle. So that is a 5. We're going to get a 6-4 pair here, and this is definitely okay as a contiguous combination. Now that's quite interesting. This is 1 or 3, and that needs a neighbor, so we have to have either 2 or 4 here. And in fact, that cell can't be a 4, because it would need a circle because of that one. So that's a 2. That gives us 2 over here. The 2's done. Yeah, that fixes this 1-2 pair. They're all resolved. 1 is going to end up in one of those 2 cells. And in fact, weirdly, we can tell which one, because this one can't have a neighboring 2. So 1 goes up here. That's sorting out 3 and 1. I think we're on a bit of a roll now. 1, 9, 4, 2, 6. So that 2, it's got its neighbour. That's all right. This 9 still needs an 8. Can't resolve that yet. This is going to be 3, 4, and 8. Now its only place for a neighbour is right here. So that's going to have to be a neighbour. So this can't be a 3. As this can't be a 2 or a 4. If it's a 4, this is 3 or 5. It would have to be 3. If it's an 8, it would have to be a 7. So 3 or 7 there, certainly not 6. And we can place the 6 accordingly. It must be here. Now, I'm probably not quite using the circles enough. Right, this needs a neighbour. 3 must be in one of those 2 cells, which is quite good for being next to the 2. This one now, Christ's head, is 4, 5, 6, or 8. And it has a neighbour here. Not many of those are impossible yet, I don't think. Can't see it quickly if they are. Now, these can't be 5. We've got a little 3-8 deadly pattern here, so we'll hope that gets resolved. This becomes a 4 because of that 3-8 pair. This becomes a 5. We can take 5 out of all those as possibles. Therefore, out of these counterpart cells, this can't be a 4. That 3-8 pair is sorting this out as well. That's another 5. That can't be a 5 because of the Knight's move to there, so 5 goes in up here. We have 4, 6, and 8 in the top row still to be sure about. So where does 1 go? 1 can't be here, and it can't be here because that would need a circle. So 1 in box 3 is here. That tells us where 4 is. That says its neighbour is 3. Now we have 7 and 8 here. This doesn't need to be 8 anymore. And indeed, it can't be 3 anymore. So 3, I say the 2 needed 3 as a neighbour. It doesn't because it's already got the 1. So I'm taking. Oh no, that 3 needs a 3 in a Knight's move away. So that is a 3. 4 and 5 can go in. 6 and 4 have been resolved. That's a 6, 8 pair. This is a 7, so that's not a 4. Still haven't quite got the head sorted out there. The 7 will get neighboured by that, so we don't have to worry about any more neighbouring issues at the top. This is no longer a 3, and I think the rest is probably just Sudoku. 7 there is a neighbour to, is a knight's move to that 7. This is now 3, which is a knight's move to that 3. Let's remove the colours there because we just don't need them anymore. This one is not 3. That 4 needs a neighbour, that's what it is. Needs a knight's move neighbour, that is. So 5 and 8 still to go in the bottom row. 1 and 8 in, oh, that's the 1, that's 8, they're all done. Now 3, 7 and 6 to place here, that's the 3 because of 7 and 6 there. We can actually do the 6 and the 7 straightforwardly. That's fixed. Jesus' head is an 8, we get a 5 here. 8 there, 5 and 8 down here, and then we just have this deadly pattern to resolve, and that 8 sorts it all out because this would need a circle if it was an 8. So the 3s go in and the 8s go in. And it was pretty tough actually, I didn't find that easy, but that's how to solve Christ the Redeemer. This is the fortress puzzle. So blue cells have to be bigger than the white cells they neighbour. And that's very useful. We've got 3 digits where the white cells are quite large next to a blue cell. So this one has to be bigger than 7. It clearly can't be 8 in the row, so that's a 9. This one also bigger than 7. Now there's a 9 in the box, so that's an 8. This pair over here are both bigger than 6 and can't be 9, so they must be a 7-8 pair. Similarly over here we must have a 7-9 pair, so that's a decent start. Now look at where the 5s are. This is quite interesting because 4 of them are looking into the central box and in fact ruling out all the blue cells, which is going to put a 5 in the center cell just by Sudoku. Now that may surprise you. You may have looked at this central box and gone, well, there's only one white cell. Which number is smaller than all the others? It has to be 1. But that ignores the fact that these 4 cells are really not acting as fortress cells at all because all their neighbours are blue. So they're allowed to be as big or small as they like. They're not affected. So in fact, all you knew from looking, if we had no given digits, you'd know that this number was no more than 5. But actually, given the position of the 5s, you know that it is a 5. I'm also going to pencil mark in 5s in boxes 1 and 9, given those 5s that we got in the original. So here we go. Now, what next? This 4 needs bigger numbers around it. They have to be from 6, 7, 8 or 9 because 5 is already in the box. That one can't be a 9. But now we're going to have to think a bit more. So what we've got in boxes 4 and 6 especially is the numbers 5, 6, 7, 8, 9 all effectively placed. So the others have to be 1, 2, 3 and 4. And we may as well candidate mark those in. I mean, we could have gone for small numbers but with shading, but that would probably mess up with the blue, so maybe best not to. Now we also know that this 5 is smaller than the numbers that surround it, and that's quite a big deduction in fact. 6, 7, 8 and 9 have to go in there. This one can't be 9 or 6. This one actually can't be 9, 6 or 8, so that's a 7. And in fact that means we can place this as an 8. We have a 6, 9 pair flanking here. Now that's useful because it turns this one into a 7 and this into an 8, and we're disambiguating all the blue high numbers now. This one now can't be 8 or 7, that's a 6. This one can't be 6, so we may stop a bit short there. We've got this 6, 9 pair here. Again, let's put in the 1, 2, 3, 4 possibilities, although 4 can't be in column 4 where there's already a 4. And we get to this stage now. Now let's keep remembering the fortress constraint. This one has to be less than 6 and it can't be 5 or 4, so it's 1, 2 or 3. This 1, again, don't be tempted to think it has to be here in box 2 because it can still be there. So I'm going to pencil mark that into those two. Similarly, it can't be in that cell, so that's not a 1, but it can be in either of those. Now, this is 2, 3 or 4 and has to be bigger than this, which actually can't be 1. So that's 2 or 3, and this is 3 or 4 there. Let's see what else we can do. 1, 2 or 3 there. And 1, 2, 3 and 4 at the top, but not 1 at the very top. Now 4, 6, 5, 1, 2, 3. Now here's a very interesting point about this cell. If this is a 3, then this has to be a 4 to be bigger, clearly. And that makes this a 2 because it's in the same box as where the 4 has now been placed. If, on the other hand, this is a 2, where does 2 go in box 4, box 6? It's got to be there. So whatever this is, it's a sort of Schrödinger moment. We don't know whether this is a 2 or a 3, but we do know that it forces a 2 over here. So we can put that in. That's possibly one of the more difficult steps in this puzzle, in fact, is to find that 2. That means that 2 is now down here somewhere and therefore not in these cells. 2 must be up there somewhere. Now this has become 9 or 7 just by Sudoku, given everything that it's looking at. This is in fact a naked single. 1, 5, 2, 8, 3 in the column, 4, 9, 7 in the row. So that becomes a 6. We have 4, 7 and 9 to go in the other cells in the column. Now let's have a look across the column here. 6, 8, 9, 7, 4. Not quite as helpful as I was hoping. 6 there. Oh, now that is interesting. 6 there and 6 there. Where does 6 go in box 1? Well, there are 2 cells left. Bear in mind the 6 there. So there are 2 cells left where it could go. But what would happen if 6 was here? Well, that would need a higher digit here, but 7, 8 and 9 are all gone. So 6 is definitely here. Now by Sudoku in row 3, 6 is in the blue cell. That means we've fixed the 6, 9 pair in the middle. This can't be 9 anymore. And again, good progress made. Now this can still be 5. Let's keep looking around the blue cells. Aha, here we have a small number, but it's got to be bigger than the small number here. So this is 1, 2 or 3. That's 2, 3 or 4. 2, 4, 6, 9, 3. Right, 9 and in box 8. We've got those 2 9s. So 9 has to be in one of those 2 cells. Well, it can never be in that one, a white cell next to a blue one. So we know that 9 goes in there. Can this be the other of 7 or 8? You see there's 1 of 7 or 8 there, 2 white cells left. Can this be 7 or 8? No, it would be bigger than that 6. So we end up with a 7, 8 pair. This is from 1, 2 or 3. It can't be a 2 because of that positioning. Now we know that 2 is in one of these cells. Looking up at these, so they can't have a 2. And this one, we've got 5, 6, 7, 8, 9 both in the box and the column. That now has to be 2, 3 or 4. This one is 1, 2 or 3. Still looking for 5 is in one of those 2 cells. Not sure which yet. And really the fortress stuff has come down to this being bigger than these 2. And this being bigger than this. That's all we have left to do in terms of fortress. Now, this clearly can't be a 4, or that would be a 3, and they'd be the wrong way round, so that's not a 4. Now 4 is in one of these 2 cells. Can we use that? Possibly not. No? Okay. Let's find out what else we can use. 9 has to be in one of those two, in box 9, given the two 9s we have here. And let's highlight all our 9s and just see if they're telling us anything else. Aha, they are in box 1. That's quite interesting. 9, we can see that the cells we've got highlighted rule out those ones, obviously not in those cells, but interestingly this cell is also ruled out by the fortress rule. This has to be below 6 or 7, so I was wrong about where the only fortress constraints left were operating. And now that's very interesting. With 9 there, 9 here, 8 there and 8 there, we know that 8 and 9 in column 3 have to be in the bottom box, and they must now form a pair down here. So these ones are from 1, 2, 3 and 5. 4 must be in one of those two cells in the column, therefore we can take it out of that one in the box. Now can we use this 8, 9 pair? 6. Oh yeah, where does 4 go in this box now? We can certainly use that. Look at these two, only 2 4s achieved, but they rule out all of these cells, and now we can place 4 in the box. Has to be there. That's giving us a 4, must be down here. It makes this one not a 4. So that's 7, and we can finish the column with a 4 up there. I don't know which of those is 4, but I know that one isn't now. And in fact, look at column 5 now. We've got a 1, 2, 3 triple, so that's the 4. We can take it out of that cell. Yeah, that's pretty handy. Now, 9 over here is in one of these two, sort of forming an X-wing with the 9 over there. And in fact, this 9 that we got has fixed the 8, 9 pair down in box 7. This is a naked single now, 5, 8, 4, 6, 2, 9 in the row, 3 and 7 in the box as well. 1 there, and that's really helping with the disambiguation of the small numbers. So they're all getting sorted near the top. That can't be 2 or 3, that can't be 3. We've got a 1, 4 pair in the central box, so this becomes 3, 2 here. I can just see there were other ways of doing that too. Now, 7 to finish row 8, should have done that before. We've got a 9, 7 pair left in column 2 in box 1. These don't have a 5, so they're from 1, 2 and 3. That's not 3, that's not a 1. This, look, we've got a 3 there looking at this 2 or 3 combination. So that Schrodinger cell that really got us going is resolved now. 2 there, 1, 6, 4, 2, 8. 7 in this box now has to be here. And that gives us the 7, 9 disambiguation. That fixes this as a 9. That's sorted out all our 5s remaining suddenly. 5 there, 5 there, 5 there. This one is not a 5 or a 1 now. It's a 2 or a 3. That forms a nice little pair there. So we can put in 1, 3, 2, 3. That's not a 3. So we've got a 1, 2 pair in the row now. Oh, and actually 7 and 8 have been disambiguated by the 7 over here. We've got 6 and 3 to place in row 7. That's relatively straightforward. That's a 1 or a 2 in the box. That's leaving 8 and 4 in these two, which are straight in. This one's a 3 for every possible reason. 1 there, that's not a 1. Now we're getting left with some pretty tricky patterns at this point. So what can we still do? Oh yes, look, that 3 is looking across at this. So 4 there, 3 there. That 4 sorts out the 1, 2, 4 pair in box 4. And I think everything else is on the road to solution now. And we are going to be done with Machu Picchu. There we go. Let's click the tick. And that's all good. So, excellent. That is the Machu Picchu puzzle done. We can move on to puzzle 6. After that comes Chichen Itza, the Mesoamerican what is it, a temple in a step pyramid in Yucatan. So for us, though, the important thing is that this is a form of a snake puzzle, although a relatively simple one, happily, because the more complicated ones are pretty tough. So the rules are that a snake of digits from 1 to 9 runs down the staircase. On one side, the digits are in order, and on the other, they are out of order. So if that rule set has survived, we get the lines, and we know that on one side of this staircase, the digits run in order. Now, it did say run down, but let's just assume that the lines give an order one way or the other. Now, the pretty thing about the corners is they both see ones. So clearly that's not the end of whichever snake is in order that is a 1. So there must be a 1 here, there must be a 2 here. One of these is a 3, because on one side or the other, the snake goes down in order. Similarly, one of those is a 4. I'm going to pencil mark one of those as a 5, one of those is a 6, one of those is a 7, one of those is an 8, and one of the end ones is a 9. Now, I wouldn't normally do pencil marks across boxes, but it's quite important that we try and remember for these cells that one of these snakes is in the right order, and we'll have to try and figure out which one. So let's do a bit of ordinary Sudoku with the rest of the grid. So we could have got that 3 was there from Sudoku. 4, I don't know, maybe these pencil marks are going to mess with ordinary Sudoku. So actually, on reflection, I'm going to take them out again. And we'll just try and remember that if we get any definite numbers on these stairs, it's really going to help. That's the most important thing. I should mention, I don't know if you will have spotted in the blurb for the puzzle, or if you might have known from your own knowledge, that one of the staircases of El Castillo, the significant step pyramid in Chichen Itza, actually has serpents designed on it, and also creates the image of a serpent with the evening sun using the shadow, which is absolutely fascinating. It's disputed whether it's definitely deliberate, but it occurs, and it's world famous, and I think that's why we were inspired to put a snake on the staircase here. Now, 3 is a very useful number here. It rules out those 2 cells, so we can put a 3 in one of those. Then it looks across and rules out those 2 cells. So now we know 3 is in one of those 2 and must be down here, along with a 2. Now, we haven't quite managed to rule out that that corner is a 9. Let's have a look along row 5, where does a 4 go? Well, interestingly, it's ruled out of all of those empty cells, so we can place it here. That's going to give us a 4 down here somewhere. We've still got 6, 7 and 8 to place in the row. I'm going to mark the candidates because they may be useful. 1, 2. I'm going to put the 3 in because that's not in dispute. And actually, remember that a 4 was in one of these 2 places, and they are within the same box, so I'll leave that pencil mark in. It enables me to take 4 out of those 2 cells. And that's suddenly very interesting, in fact, because these 2 cells now have to have a 4 in. What's that telling us? It's telling us that this is not the snake that's in the right order. So we can suddenly fill in the whole of the snake that is in the right order over on the right hand side. In it goes, and all we now know about this line is that it contains the digits 1 to 9, but we don't know the order, except that none of them will obviously match in the rows over here. Let's just keep going with Sudoku. We've got 5, 8, 7, 6, 9 here, so we can put the 4 in now into this box, and the 1, and we get a 2, 3 pair here. 9, 2, 3, 4, 6, 1. We've got 5, 7 and 8 to place. This one can't be the 3 anymore, and that means we know where the 3 is in box 3. It's over here. This can't be a 6 anymore because of the snake 6. That's enabling us to finish a lot of box 6. Just a 6, 9 pair left. 2, 5 pair at the top can be filled in, and we know this is a 7 now. Now we can look along the rows where this one's 6, that's definite. 4917. This is 4 or 5. This is 3 or 4, and this is 3 or 5. 9, 3, 4, 7, 8. 1 is in one of those two cells in row 2. And we've got 3, 7 and 6 to place in row 1, but not much idea about where to. So let's go down and have a quick look at this box, 62437. So 1 can be placed. Actually, that's quite big. 5 must be down in one of those two, 9 in one of the corners, and 8 could be in any of them. Right, so let's have a look at this snake again. This can't be 1, 2, 3, 4, 7 or 5 or 9. So that's 6 or 8. This one cannot be a 4 anymore. Let's get rid of that marking. But there's a lot it can be, so I'm not going to focus too much on that yet. Let's have a look down here. This one, for instance, sees 4, 1, 6, 7 in the column. 8, 9 in the row. 2, 3 or 5 remain. 7 can't be there anymore because of the 7 on the snake. Actually, let's have a look at this cell. 5, 6 or 8 up there. Be nice to place another digit on the snake just to increase the amount we know about it. Now, this cell can't be 4, 5 or 1 in the row, 7, 3, 2 in the column. So that's 6, 8 or 9. This one similarly 4, 5, 1 in the row, but that's all. 2 on the snake already, so it can't be that. This one, 1, 5, 8 and 9 are possible, but 1's been used on the snake. Here, 9, 1, 2, 6, 7, 3, 4, 5 and 8 still possible. And here 3, 5, 6 and 7. So are there any places on the snake where there's only one place for a certain digit to appear? Not really, actually. Yes, 4 actually. 4 is the lone digit that we can place in one given cell on the snake. It cannot be here because of this 4 that we put in over there. So the 4 on the snake has to be here. 2, 3, 1, 6, 8, 2, 7, 3, 4. Now, yes, we've got a 5, 6, 8, 9 quadruple, which is revealing to me what I could have learnt another way. Where does 1 go in the column? Well, it's got to be here. Can't be on the snake because we've already had a 1 there. That's going to give us a 1 in one of those two cells in row 8. 4, 5, 1, 4, 9, 8, 4, 1. Okay, I'm not finding it easy, but I have noticed that 3 is ruled out of all of those cells. So 3 must be in one of these two cells in box 2. That means it's not here. That's not quite giving us a 6, 7, 8, 9 quadruple. Although if I could get 7 out of this cell, we'd be well on the way to it. Now, 5, 1, 9, 2, 3. We've got, these are from 4, 6, 7 and 8. They must include 4 and 7. That one's not an 8 though. 2, 7, 3, 4. Actually, I'm glad this puzzle's holding up because I was a bit worried this was too easy. Now, in fact, no, happy enough with it. 9, 8, 4, 1. Interesting. Okay, let's... What can we do next? 3, 4, 7, 9, 1. This is now a 1-2 pair rather than just a possibility of either, because 1 and 2 are there. So we have 5 or 6 here, 5 or 8 here. Can we use that in any way? We know 3's in one of these cells. That's not very helpful down here. Still don't know about this being 2, 3 or 5. Wow, okay. 6, 5's in one of those. Now maybe there's a cell where all the possibilities on the snake are looking at it. That would be useful, wouldn't it? Oh, I said this could be a 2, but there's a 2 on the snake. That was very wrong of me. Okay, so we'll take the 2 possibility out of there. 2 is now confined to those 2 cells in box 7 and those 2 cells in box 9. So the 2 in box 8 must be in one of these 2. This is now 3 or 5. Have we? 7 can only be in those 2 cells. And that's quite interesting. The 7 on the snake has to be in one of these 2 cells. None of the others are possible because of the given 7s we have and the numbers filled in on the snake. These 2 cells are both looking at that cell. So whichever one of them is the 7 on the snake, that is not a 7. So it can't be a 7. And now suddenly the only place for 7 in, it shouldn't be there, in column 2 is down at the bottom on the snake. So that is a 7. This isn't. Now we have a 6, 8, 9 triple on the snake. That makes this cell a 5, this one a 3. Now we're cooking with gas. We've got a 2, 6, 5 triple down here. Not 2 there, not 5 there. That means this is not a 6. 2, 5, 6, 1, 9, 8. These 2 cells see those 2, 5, 6 in the box. They both see 4 in their rows and they see 1, 9, 8 in the column. So they're 3 and 7. In fact, this was a naked single 3. 7 goes up there. That 3 has sorted out the 2, 3 pair. That sorts out where 2 goes here. We've got 6, 8, 9 still to go in box 7. 2, 5, 6 still a group. 3, 7. The 2, 5, 6 triple has made that one. No, that's 8 or 9. I misread the pencil marks. So we've got 1, 8 and 9 still to place in the box. Don't quite know how that goes yet. Right, we've got a 5 here, so these 2 can't have a 5. Now this 8, 9 pair in box 4 tells us where the 5 is there. That means we can finish the column, 3, 6 and 8 there. Now we can finish box 7. Now we can finish the snake. Now we can finish columns 1 and 2. And we are getting a lot of information for the rest of the puzzle. That's 4. Actually, we can suddenly finish column 5 as well. We're left with these pairs down here of a 1, 8 and a 2, 6. These ones can't be 4, 8. That's a 6, 7 pair. That's helped me resolve that. Wasn't necessary on their own. Now, this is now a 4 with a 5 here. We can probably do... yeah, this is a 7, this is a 3. The 7 finishes box 5. That finishes row 9. And now we can finish off the whole puzzle. And there we go. That is Chichen Itza completed. Let's click the button and we can move on. So this puzzle is Petra, and interestingly, this one hardly changed. It changed in a very small way between its composition and after review. But the reason it changed was quite amusing, and the way it changed turned out to be quite dramatically making it harder for people. So the intent here was that this be solved as an alphabet Sudoku, where you use the letters of Petra, C, D, I, and Y to compile a Sudoku puzzle. And my real intent was that you print it out and you solve it with letters. Now, people don't like doing that. I'm okay with solving a puzzle with letters, but most people really want to see numbers. They get used to them in Sudoku grids. I do understand that. And the document, of course, had a explanation that the middle row of Petra Petra appears 5 times in a straight orthogonal line in the grid. The 4 coloured cells contain the same letter. Ultimately, the grid can be converted to numbers by knowing that the central row represents 1, 3, 4, 9, 5, 2, 8, 6, 7. So those are the rules. Let's just put the numbers, well, I'll put them somewhere I can see them for now, but anyway. Thanks. So Windows for trying to be helpful and being quite the opposite. Right, there we go. So a lot of people thought that the best way to solve this is to fill in 1, 3, 4, 9, 5, 2, 8, 6, 7, which is going to be the ultimate result of the central row, and then try and work out, you know that 6 equals I now, you know some of the things that A doesn't equal. We'll try and work out what letters represent numbers and work it from there. And some people did that successfully. And my hat is off to them, because that is not how I would solve this puzzle. I think the simplest way was to just choose random numbers. If you want to do it with numbers, and a lot of people do, I understand that, but let's choose random numbers, represent the letters in the grid with those random numbers, and solve it, and then substitute at the end so that the middle row reads 1, 3, 4, 9, 5, 2, 8, 6, 7. So that's the way I'm going to do it now. Now, one of the ways you could do that with numbers is just enter 1, 2, 3, 4, 5, 6, 7 down here. You will note that there's P and A of the letters we're going to have to use left over, and this one can't be an A, so you could put those in as P and A. Now that would mean that every string of Petra that we have to find is going to be 8, 2, 6, 1, and 9, because that's what A must be. But that's not a very memorable string of numbers. So in fact, I'm not going to do it that way round either. I'm going to make Petra 1 to 5. P, E, T, R, A. Now how do I know that that's P? Because it can't be any of Red City or A, so it must be the other number. Right, so I'm going to use these number equivalences and try and solve the puzzle this way. So let's fill in the other numbers that gives us. We'll have to just make up 6, 7, 8, 9 for D, C, I, Y. That doesn't matter so much at the moment. So RID is 4, 8, 6. So those are the givens that we get. And with this puzzle, Petra now is going to be 1, 2, 3, 4, 5, and has to appear 5 times in the grid in an orthogonal row. So with this puzzle, you have to just think a bit about how this can possibly work. And the intent here was that you look for 1, 2, 3, 4, 5s in that order, so either running across or down. Now, some people wondered whether 5, 4, 3, 2, 1 was ruled out, like a word search, so that it could run that way. And that wasn't my intent. I'm told that you can work out that it can't happen like that. One of the more common advice pieces on the Puzzle Hunt discussion thread of Discord was that the rules would have said RTEP if that was one of the possible ways that Petra could be written in the grid. And I think that's a reasonable assumption. So the intent is Petra can either be written 5 cells across or 5 cells down, 5 times in the grid. Now the first thing I think you have to work out is, can some of the Petras be across and some be down? Bear in mind, we are now looking for the number string 1, 2, 3, 4, 5. So the way I consider that is to wonder how that would work in terms of where would you see 1, 2, 3, 4, 5? Would they cross each other if that happened, if there were some across and some down? Now, if they did cross each other, remember that to fit in a 5-digit string, we're either going to have to start in column 5, 4, 3, 2, or 1, or row 5, 4, 3, 2, or 1. There's no other way. So the only possible starting cells for all the Petras are in this area. Sorry, that's not true. Let's get this right. Possible starting cells for Petra are in this area. They could start anywhere here. They couldn't start in these cells because there wouldn't be enough room to write Petra. Now, if there was going to be can the Petras run both down and across? Well, if there was a Petra running down, could it be in column 1? It would have to go 1, 2, 3, 4, hit the 5 there. Impossible, because the 3 would be in the same row as a 3. Can it be in column 2? No, because the 4 is below the 5. Can it be in column 3? No, because the 5 is going to end up in a clash with another 5 in the grid. So there's no way it can be there. Now, what about in column 4? Well, the same actually is going to apply to a lot of these columns. It clearly isn't written in column 8. If it begins in column 1, the 2 is going to clash with that 2. It could theoretically begin in column 2, but the 5 is going to clash with that 5. If it began in row 3, that's what I'm trying to say here, well, this is just possible. We could get a 1, 2, 3, 4, 5 in quite a few of these positions, not in these cells because the 3 would clash in the box. So those seem to be 3 cells where 1, 2, 3, 4, 5 could be written. It couldn't start here or in row 4 or in row 5 because the 5s would again clash. So the only possible positions the down Petra could be written is in those. Now we'd still have to fit in 4 across Petras. Now, could they start from the same cell? Definitely not. Could they cross in the same cell? Well, definitely not, because anywhere you can envision a cross, you're going to get a clash between the 2 versions of Petra apart from this position, where you could just get 1, 2, 3, 4, 5 written in both places, and it would work. Now, actually, maybe that's not true. Maybe you can write it here, 1, 2, 3, 4, 5. Yes, you can. The problem with this is this will be the only down you can fit in. And now you have to fit in 4 acrosses of 1, 2, 3, 4, 5. And you will find that there is just no way to make that work. You can get in 1 there, but not. That's going to clash with the 1 that you've put in one of these cells. So you'd have to start any 1s in the top rows with a 1 in this box, because those would have been ruling out all of these places. You just couldn't fit them in here to cross with the 1, 2, 3, 4, 5 you were putting in one of these cells, and it's just not going to work. So there is no way to do that. So what that is telling us is, in fact, that all the 5 1, 2, 3, 4, 5s or Petras are written across the grid. And we then know that they must start, one of them in column 1, one of them in column 2, one of them in column 3, one of them in column 4, and one of them in column 5 to fit in and not clash with each other. So that's quite interesting. Now, what that also tells us is that in each group of 3 boxes running across the grid, there can be only 2 Petras, because otherwise 2 of them would start in the same box. So in fact, this arrangement's impossible because you'd have a 1 in this cell and a 1 in this cell. So maybe you could, in theory, have something like this. I mean, we'll work out what does and doesn't work as we go along. And what this does mean is that one of the Petras starts in column 5 and must run through this list of all the digits, and it must hit the 4. So we can fill that in the top row. It has to be there. Another one must end in column 8, so that's got to be the 5 down here. So we've got 2 of the Petras done already, no problem at all. And we have 3 more to fit in. 1 more could be in those cells. Up to 2 could be in these ones. And 1 more could be in those. Now, rows that cannot possibly have 1, 2, 3, 4, 5 written in include that one and that one because of where the 5s are pitched, and that one because of where the 2 is pitched. Now, given the positions of 7 and 8 here in rows 4 and 5, in fact, we can work out that only one of these rows, row 4 and 5, can possibly have one of these Petras, because it's going to have to start in box 4. So therefore, one of them's there, one of them must be in row 3, and one of them must be in row 7. Now we can also see, where does the one in row 7 go? Where can 3 go in it? Well, it can't clash with this box, so you'll find it has to be starting in row 7, column 1. So that's another of the Petras. Let's colour that green as well, because that's definite. And there's one in row 3. And remember, the 2 doesn't allow a 2 into this cell. So this now has to start here. And that's 4 of our 5 Petras are in the grid. The 5th one is going to either be here or here. So I'm going to pencil mark in the 1s, the 2s, 3s, the 4s, and the 5s. There must be, one of those is a green Petra. We don't know which yet. So here we go. We've got tons of starting digits for our puzzle now, and we can just do some Sudoku to get going. 6, 7, 9, triple there gives us an 8 here. That 8 in row 7 must be there. 6, 7 pair there. We can fill in 2 and 3. We've got a 9, 7 pair to go in here. I'm not worrying yet about the purple cells. We'll get to them in a bit. 1, 7, 8, 9 to go in box 3. Those can't be 1 and those can't be 8. What else can we see? 5 and 5. We can place a 5 here. And we've got a 3 and, in fact, there's a 3, 4, 5 triple. So we can fill those into row 2 like that. Remaining digits are 6. In fact, for both box 1 and row 1 are 6, 7, 8, and 9. A couple of those cells can't be a 6. In fact, I think they must be the same digit. These ones will also be from 6, 7, 8, 9. That can't be a 6, and that can't be an 8. Now, let's have a quick look at this other purple cell, just in case that can tell us anything. The purple cells are all the same. This one can't be an 8. These ones, if they're to be the same, and it can't be an 8, we can tell that purple is now either 7 or 9. So let's restrict all the purple cells to 7 or 9. Gives us a pair in column 6, and that makes this a 6 up here, which is surprising but useful. Then we have a 1, 4 pair going on in here. The 4 is in the Petra row, wherever it is, the 1 isn't. Let's see if we can do a little bit more Sudoku. We've got 8, 8, we now know this is an 8. That can't be an 8, so the 8 in box 2 is there. Those can't be the 8, so the 8 in box 1 is there. Now we can actually place the 8 in column 2 as well. It's got to be here. And 7, 9 pair in the central column. So this is 8, 3, and 6. We can put in 8 and we have a 3, 6 pair. Let's just keep going with some regular Sudoku if we can. This one is now a 1, it has to be. This is 6, 7, or 9. And we're beginning to slow down a bit when we still have not identified either what the purple cell is or where the Petra is. That's something that we're going to have to try and figure out in a moment. So we just have one more look. 3 is definitely in one of those 2 cells. 6, 1, this is a 2-5 pair, is it? That can't be 5. Yes, it is. Which gives us a 7-9 pair in row 6, where we now have 1, 2, 4, and 6 to place. That's 2 or 6. That's 1. Oh no, this can't be a 1 because the Petra requires a 1 in one of those. So this is 4 or 6. So in fact, we know where the 1 goes in row 7. It must be here, thanks to the Petra information, as it were. Now this is an X-wing on 7s. So 7, and I mean we've got that 7 there, so these cells don't include 7. They must now be from 5, 6, and 9. And the really interesting question at this point, I think a lot of people, having got this far, then felt they had to bifurcate, and they either guessed what the purple cell was or where the Petra was. But you don't actually have to do that. You can wonder what happens if the 6 is in one of those two cells. There is clearly a 6 in one of those two cells. If there was also 6 in one of those two cells, then neither of these could be 1, 2, 3, 4, 5 if both of those had 6s. So 6 cannot be forming an X-wing with 6 there. So you can't have a 6 there. That's now a 5-9 pair. Suddenly we know that the purple cell is a 7. That enables us to do a fair bit more Sudoku on the rest of the grid. 7s can't be there. These are from 2, 4, and 6. That 7 makes this a 9. Now we still haven't resolved which of these is 1, 2, 3, 4, 5, but we know that the other side of it is going to run 5, 6, 1, 9. And that's quite interesting because if this ran 5, 6, 1, 9, this couldn't be filled in. So suddenly we do know that the 5, 6, 1, 9 part, the non-Petra part of this 10 cell area, must be up here. So we can fill in 5, 6, 1, 9 there. Now we can put in the last Petra, 1, 2, 3, 4, 5. Color it green to show where all the Petras are. And that is now a 6. Oh, sorry, I accidentally colored that. That is a 6, I say. Right. So take this out. This is now a 9. 7 here. We can place 3. Take 1 out. This has become a 6 down here. And this is now 4 naked symbols. So that finishes off the grid. Now I say finishes off the grid. We obviously still have a conversion to do to get back to the requirement in the preamble. So let's have another look at that. And this has all been necessary because our software doesn't do letters, I'm afraid. But that's what we have to work with. Now, it said that the central row represents 1, 3, 4, 9, 5, 2, 8, 6, 7. So let me just see if I can keep that in shot. There we go. So we're going to try and convert to that. Now, how can we do that? Well, with the new software, you can at least highlight individual digits and do things with them. So first of all, I'm going to highlight all the 7s and remove them from the grid. And their pencil marks, all of their pencil marks. There we go. So the 7 spaces are now blank. And in the end, they are going to end up being the first digit. They're going to be a 1. But first of all, let's see where we can put in 7s now. They go at the end of the string. So all these 6s are going to become 7s. Now, where are 6s going to go? Well, they're here. So they become 6s. 8s, this is very handy. We're working back along the line. Then we're going to put in 5 somewhere. Those are the central digit of the central row. Then we've just taken out 3. Where's 3 going to go? It's going to replace this 9. Where's 9 going to go? It's going to replace this 2. Where's 2 going to go? It's going to replace 4. And where's 4 going to go? It's going to replace 1. And these remaining digits, I should have colored them at the beginning, but they're all going to be 1s. And that quickly finishes the grid again. So we just check, looks good to me, and we now have the central row reading 134952867, which is what we needed. So there we go. That is how we get through Petra, and we get on to the final puzzle. So let's just have a look at the document and what the final puzzle says. Let's just move it. Each marked line is a palindrome with digits in the same order from each end. 3 digits must be transferred from equivalent positions in each other puzzle. And here, well, how do we know which 3 digits from each other puzzle? The only real clue we have is 7 different groups of colour. So if we look back at the other puzzles, well, there's some purple markings in the Petra one. And look, Petra's written in purple. Red markings in Chichen Itza. Chichen Itza is written in red. Blue markings in Machu Picchu, which is also written in blue, etc., etc. So blue, red, and purple look like they're Machu Picchu, Chichen Itza, and Petra. And if we, so at the beginning, I think, 3 digits must be transferred from equivalent positions in each other puzzle. That's what it said. So let's nip through the other puzzles and transfer the digits. So we'll start with the completed Colosseum. There we go. So actually that's yellow. So what digits do I need for yellow? I need the ones starting in row 3, column 6. So they are 6, 5, 9. So we'll fill those in. 6, 5, 9. If we do this right, we won't get any clashes in this grid. The next one is a green line, so we need green digits starting in row 7, column 2, and they are 9, 6, 1. Okay, so we'll put those in. After the Great Wall of China comes the Taj Mahal. That's grey. That's up here in row 3, column 4, 9, 8, 4. We can fill those in. Then it's Christ the Redeemer, who I remember is orange, 8, 7, 4 at the top. Then we have Machu Picchu, which is blue, so from row 5, column 3, 1, 4, 2 there. Fill those in. Red, sorry, which digits do I want? There from here, 715 from Chichen Itza, 715, 5, and the purple, which is Petra, 348. Now, the reason that we made Petra so hard for you to do was because if we'd given you what the correct numbers were straight away, you could have filled in 2971653 there. Well, you could have actually worked out that with A being 8, you could have done the 348 instantly as the first deduction in solving this puzzle, and then worked out that that's what you needed to transfer over. So I'm afraid we couldn't make it that easy. The other interesting story about putting together the hunt was we changed, as you heard, the Christ the Redeemer puzzle quite considerably. Obviously, we had to leave 8, 7, 4 the same. In fact, the grid from the original Christ the Redeemer turned out to be the same as the grid from the final Christ the Redeemer, because the rule set worked fine with the puzzle grid that we had originally. So although I spent quite a lot of time trying to improve the grid, in the end I ended up using the same grid for Christ the Redeemer. Anyway, now we have a relatively straightforward palindrome puzzle to do here. So this palindrome starts 4981, so that's quite easy. Haven't heard any instructions about the grey dot. We'll get to that at the end, but we can enter 4981 there. Then there's an 8 next on the palindrome, so that can go this end as well. Those 4 cells are going to be the same as those 4, but we don't know what they are yet. We'll have a look at that in a moment. Let's see what other Sudoku we can do. 1 in the central box is fairly straightforward. Then we're going to have a 7 on one end or the other. That run of 3. What else can we do? These cells are going to be from 2, 3, and 5. That one can't be a 5. So there must be a 5 in one of those two. And 2 or 3. So let's put that in here. There must be a 5 and one of 2 or 3. That's still on the palindrome as well. What else is straightforward here? 4, yeah, we've got 4 4s pointing at box 6, so we can fill in 4 there. 9 down in one of those, a 3 up in one of those. You may remember this path much better than I do, or you may be able to see it much more quickly than I can now. 4 is in one of those. 4 there puts 4 in one of those. So in the top row, 4 now has to be here. These are from 2, 3, 5, and 7. Now that's quite interesting. That can't be 7 and that can't be 7. But we now have a 2, 3, 5, 7 quadruple in box 4. These two are 9 and 6. That one's on the palindrome, so that is 6 or 9 as well. This is 2, 3, 5, or 7 by the palindrome. And we've also now got a 6, 9 pair in column 3. The 8 in column 3 can't be there or there, so we can place that. That gives us an 8 here as well. Maybe we can finish off 8s with boxes 6 and 1. Yes, there we go. They're all done. 3 is in one of these two. Quite how that's working yet. We've got a 2, 3, 5 triple in the row. Oh, look, we've got 9 looking at that. Sorry, that's much more straightforward than I was realizing. That can go straight in. The 1 is the number missing from row 2. It's going to put 1 there is going to force a 1 into one of those. So the 1 in row 3 can also be written in now. So can 7 in column 8. We've got a 2, 5, 6 triple here, which doesn't have 5 at the top. Therefore, this is a 3, 9 pair, which can be filled in. This can't be 3, and it's on the palindrome. 9, no. Right, this cell has to be the same as this one, and between them they see all of everything except 7, so they're going to have to be 7s. This one can see 9, 5, 8, 1, 4 in the box, 6 in the column, and this one can see 2 and 3 in its row. So they're both, the only possibility left is a 7. This becomes a naked single 4, which gives us a final 4 down here. This now is a naked single 6. We get a 1 there. That's the last 1 in the grid. We've ended up with a 1 on the grey dot. We don't know what that means yet. 6 there, puts a 6 here in box 5. We've got 2 and 3 still to go in box 5. 5 and 9. Bottom somewhere, that's part of a 2, 3 pair. 7, 9, 1, 8, 4, 3 in one of those, 5 in one of those, 6 up at the top somewhere. Do I know that one of those is a 2? No, not necessarily. 4, 6, 1, 8. 9 is actually placed. I hadn't noticed that I disambiguated that. And now 2 in column 1 has to be in one of those cells with the 5. So it's a 2, 5 pair. And up here the same must be true on the palindrome. So that becomes a 3 in the box. It's not a 3. These aren't 2 and 5, so we can fill in 3 and 7. The 7's also on the palindrome. That's a 2, 5 pair in box 1 as well. So 3 there. 5 here, that sorts out 9, 5, that fixes the 9. We've got a 3-7 pair to go in down there in some way. We are very much nearly finished here. That's a 2. We can finish with 6 and 5. So now we can do the central rows, 2 and 3 there. We've now got this resolved as a 2, 3 there. That fixes box 7. 7 there. We've got 2 and 6 to go in at the bottom. I don't know which way around they are yet. 2, 3 and 5. So that's 2 or 5. This is the only place for 3 in row 3 now. And we've got the order of 5 and 2 on the palindrome. So we use that to disambiguate the final 2 5 pairs there. 5 and 6 to fill in here. That becomes a 2, and finally 6 and 2 there. Just hit the check button. Looks good to me. So here we are with the final grid completed. And now back to the instructions. So at the bottom of the puzzle it says the solution to the hunt is a real 7-letter word that can be decoded from equivalences used previously in the top row. Was there any extra help at the beginning? Final challenge to find a 7-letter word. The last takes 3 digits from each other puzzle. So no, not really any extra hints there. But at the end, as I say, equivalences used previously. Well, obviously in Petra we had a lot of equivalences. And here we can see, let's have a look at this top row, 943, 281, 675. So what are those equivalences? E, that's a P, remember. EPY, R, A, C, I, D, T. EPY, RAC, IDT, epiracid T. Well, that doesn't yield, as far as we can see, a 7-letter word. Now, you may be able to spot that there's almost a word within that, but you may also be still wondering about this grey dot. What is that doing in the puzzle? Where have we seen a grey dot before? And the place where we've seen a grey dot before is in the Taj Mahal puzzle, where there were a number of them. And some of them, well, one of them was sitting up in the top of the grid, where we remember now that all the consonants were represented by odd numbers. And they were specific odd numbers if you look at the consonants. The A's were all even numbers, but the consonants, M was 1, H was 3, T was 5, J was 7, and L was 9. Well, M is 1 and is the grey dot. And if we look at this grey dot, it's a 1. So what if that was an M instead of the C? That would still be using an equivalence found previously. And now we get E, pyramid, T. And you may notice that the structure of these 7 coloured areas is pyramidal. You may know that the New 7 Wonders of the World campaign honoured the original 7 Wonders of the World by naming the still standing one, the Great Pyramid of Cheops at Giza, as an honorary wonder of the world. So pyramid is the answer to our puzzle. Now, some people said, what's the ET doing around it? Well, I could tell you that that was carefully designed to represent Egypt because it is its IVR driving code, and that the pyramid is sited in Egypt. But frankly, that's just a coincidence. It was just to get the pyramid in. ET happened to work as well. Intriguingly, T was also 5 in the Taj Mahal puzzle too, which is a nice coincidence, but literally just that, a coincidence. And the answer we were looking for, therefore, was pyramid. And I cannot believe how many hundreds of people got that and sent it in. Quite a few people noticed something that happened that was deliberate originally, but we left in as an Easter egg. So the original way in which the numbers 1 to 9 were encoded. As you can see, 1 is C, 2 is R, 3 is Y, 4 was P, 5 is T, 6 is I, 7 is D, 8 is A, and 9 is E. And that spells, if you like, cryptidae, which I thought was quite a nice possible family name for the cryptid from our Tracking the Cryptid hunt. But it did inspire a lot of people who looked at the digits in this row and translated 1 to 9 in order as cryptid to assume that cryptid was the required 7-letter word. The original plan was to actually show you, or was to tell you in the preamble to Petra, that you could translate the digits using 1 to 9 as cryptidae in the end. But we preferred to leave that as, again, you could have just taken the digits 3, 4, 8 if we'd told you that without doing the puzzle at all and put them into this puzzle as 3, 4, 8. So we didn't want to do it that way. We left cryptidae as an Easter egg, and quite a lot of people found it. But it did mean that a few people sent in cryptid as the final hunt answer. Some people also sent in cryptic and decrypt for various sensible reasons, and we would tend to write back to them and tell them a little bit more about what we were looking for in the final answer and what the grey dot was doing. So that was the solution to our New 7 Wonders of the World Sudoku Hunt. We hope you enjoyed it, even if you didn't finish it. We hope you got something out of it. And if you did, and if you've watched this whole video as well, thank you very much for following all the way. Absolute pleasure bringing it to you. And thank you for being on Patreon, being one of our followers and supporting us generally. We really are grateful all the time. Bye for now.